Hello everyone, and welcome back to the series. In this chapter, we take an important step forward as we begin building the geometry of a cyclone in STAR-CCM+. Cyclones are powerful separation devices used to remove fine particles from a flowing medium, whether that medium is a gas or a liquid. They play a key role in many engineering applications where particle separation is essential. In this chapter, our goal is to create the full cyclone geometry from the ground up, step by step, directly inside the software. But this is only the beginning. In the chapters ahead, we will take this same geometry further and use it as the foundation for more advanced simulations, including flow inside a hydrocyclone, anisotropic flow behavior, and particle tracking with the Lagrangian approach. So this chapter is not just about building geometry. It is about preparing the foundation for a much deeper CFD journey. We build this geometry in SimCenter STAR-CCM Plus using the 3D-CAD modeler. This model follows the classic cyclone proportions shown in the tutorial, where all major dimensions are defined relative to one core diameter parameter, d. That means instead of hard-coding every dimension separately, we set up one master length value and use expressions based on that parameter throughout the geometry. This makes the entire model easy to scale later for parametric studies or design variations. The cyclone consists of four main parts. We have the outlet pipe at the top, the cylindrical main body, the conical lower section, and the rectangular inlet duct entering tangentially from the side. At the end, we will also assign face names so the inlet, outlet, and internal interfaces are ready for region and boundary setup later in the workflow. Let's begin. First, launch SimCenter STAR-CCM Plus, create a new simulation, and save the file as cyclone.sim. Now go to the object tree, right-click Geometry, then 3D-CAD Models, and create a new 3D-CAD model. Once the 3D-CAD environment opens, rename the default model to Cyclone. Before sketching anything, we will create the main design parameter that controls the scale of the cyclone. In the 3D-CAD tree, right-click Design Parameters, create a new length parameter, and rename it to D. Then in the Properties window, set the value of D to 0.205 meters. From this point on, most of the geometry dimensions will be expressed as multiples of D, so the model stays fully parametric. Now let's create the outlet pipe. The outlet pipe is a circular extrusion created from a sketch on a transformed plane. So first, under the XY plane, create a new plane by transformation. Accept the default settings, then select the new plane and define its translation vector in the Z direction as -0.75 times D. Rename this plane to Transform Sketch Plane. And then update 3D-CAD. This transformed plane is now positioned below the XY plane by 3/4 of the cyclone diameter, and we will use it to sketch the cross-section of the outlet pipe. Next, right-click the transformed plane and create a new sketch. Switch to View Normal to Sketch Plane so the sketch is aligned cleanly with the screen. Now choose the Create Circle tool. Place the circle center exactly at the origin and draw the circle outward. Then apply a radius dimension to that circle and set it to 0.25 times D. Confirm the sketch, then rename it to Outlet Pipe Sketch. With the sketch complete, right-click it and choose Extrude. Set the extrusion distance to 1.25 times D, confirm the operation, and rename the resulting feature to outlet pipe extrusion. Under body groups, rename the new solid body to outlet pipe. At this stage, the outlet pipe is finished. Now we can move on to the main Cyclone body. Go back to the XY plane and create a new sketch. Again, switch to View Normal to Sketch Plane. Before drawing, set the sketch grid spacing to 0.1 meters. This just makes navigation and placement easier while working in the sketch. Then create a circle centered at the origin. Apply a radius dimension to the circle and set it to 0.5 times d. Confirm the sketch and rename it to Main Body Sketch. Now, let's double-check to be sure that the origin of the previous sketch had the right center. Check the coordinate and apply fixed constraint. Now extrude this sketch to create the cylindrical upper body of the Cyclone. Set the extrusion distance to 1.5 times d. For body interaction, set it to none. Confirm the extrusion, then under body groups, rename the resulting body to main body. At this point, the main cylindrical chamber exists, but the outlet pipe volume still overlaps with it. So the next step is to subtract that overlapping volume. Right-click the main body and choose Boolean, then subtract. Use outlet pipe as the tool body. Activate both Keep Tool Bodies and Imprint. Then confirm the subtraction. Now the outlet pipe opening is cut correctly into the main body, while the outlet pipe itself is preserved as a separate body for later use. Next, we will create the conical lower section of the Cyclone. To do that, we need two sketch profiles and then a loft between them. First, make the scene transparent so we can see and access the bottom face of the main body more easily. Now create another plane by transformation from the XY plane. Set its Z translation to 4 times D. Rename this new plane to Cyclone Base Plane and update 3D-CAD. This plane marks the lower end of the Cyclone geometry. Now right-click the Cyclone Base Plane and create another sketch. Go to View Normal to Sketch Plane. Create a circle around the origin and apply a radius dimension of 0.18 times d. Confirm the sketch and rename it to Cyclone Base Sketch. Select the bottom face of the main body, right-click it, and create a sketch from face edges. Accept the sketch and keep it as the upper profile for the loft. This captures the bottom cross-section of the cylindrical body exactly. Now select both the lower sketch and the extracted face sketch from the bottom of the main body. With both profiles selected, create a loft. Accept the default loft settings and rename the feature to Conical Section Loft. While doing the loft, the body interaction setup was in the merge mode, and that is why the body and loft are merged. If you want, you can go back and change it. At this point, the main cylindrical body and the conical lower section are complete. Now let's create the inlet duct. The inlet is a rectangular duct entering the Cyclone horizontally near the top of the chamber. First, turn off scene transparency. Then under body groups, right-click the main body and choose Boolean, then slice. For the sketch plane, choose YZ and confirm. This gives us a sliced body that exposes a useful cross-sectional face for sketching the inlet geometry. Hide the sliced body if needed so the cross-sectional face is clearly visible. Then in the View controls, switch to the orientation -X up -Z so the inlet sketch is easier to define from the side. In the Graphics window, right-click the cross-sectional face of the main body and create a sketch-on face. Zoom in on the top left corner of the Cyclone body. Now project the left vertical outer edge of the main body into the sketch as construction. Do the same for the top horizontal edge. These projected construction lines will be used as references to align the inlet rectangle exactly with the outer contour of the Cyclone body. Now choose the Create Rectangle tool. Draw a rectangle near the upper left corner of the main body, matching the general position shown in the tutorial. Next, apply geometric constraints. Then apply a length dimension to one horizontal edge and set it to 0.2 times d. Apply a length dimension to one vertical edge of the rectangle and set it to 0.5 times d. Select the left edge of the rectangle and the projected vertical construction line. Then apply a collinear constraint. Do the same for the top edge of the rectangle and the projected top horizontal construction line. This locks the inlet rectangle so its top and left edges align with the main body boundary. Confirm the sketch and rename it to Inlet Sketch. To form the inlet duct, extrude this sketch. Set the extrusion distance to 1 times d. Confirm the operation and rename the resulting extrusion feature to Inlet. Now the inlet duct is added to the Cyclone Separator. At this stage, the overall Cyclone geometry is essentially complete. Save the simulation, and if any bodies are hidden, restore them so the full model is visible again. The final modeling step is to assign face names. This is important because when the geometry is later converted into parts and assigned to a region, the named faces will come in as separate part surfaces. That makes it much easier to define inlet, outlet, and interface boundaries in the simulation setup. Start by rotating the model so the inlet duct is clearly visible. Select the rectangular face at the inlet opening, right-click, choose Rename, and name it Inlet. Then select the circular face at the top of the outlet pipe, rename it, and call it Outlet. Now we will name the internal interface faces. To expose them, hide the main body first. Then select the bottom face of the outlet pipe and rename it Fluid_and_outlet. Next, select the curved baffle surface and rename it Baffle_and_outlet. Show the main body again, and now hide the outlet pipe. Turn Scene Transparency on so you can see the internal surfaces through the Cyclone body. Then select the internal circular face of the outlet pipe where it meets the main chamber and rename it Fluid_int_main. After that, select the curved baffle surface inside the main body and rename it Baffle_int_main. Finally, restore any hidden bodies so the full model is visible again. And with that, our Cyclone Separator geometry is now complete. We started from scratch in 3D-CAD, defined the whole model with the parametric diameter d, built the outlet pipe, created the main cylindrical body, added the conical section with a loft, modeled the inlet duct, and finished everything by assigning the key face names needed for the next CFD steps. So now we have a clean and fully parametric Cyclone geometry, ready for geometry preparation, meshing, and the full simulation workflow inside STAR-CCM Plus. At this point, you can close 3D-CAD and save your simulation. In the next steps, we will use this geometry for more advanced analysis and simulation. Thanks for watching, and I'll see you in the next video with another training.